from Sri Lanka, Peradeniya. Candy, right? University of Peradeniya. He basically, when we joined my lab, we worked on some biometrics problems, active authentication and how do you do continuous authentication. In fact, one of his works was featured in the CBS News. He did a lot of work on active authentication, and then for the last 2-3 years, he's been looking at some deep learning based novelty detection, open set recognition problems, and things like that. So he's published quite a lot of papers. In fact, he has published 7 conference papers, including 3 CVPR papers. And one of the papers that he published in ICPR, which is the International Conference in Pattern Recognition, he received the Best Student Paper Award. So this basically, the paper was selected among 1,200 papers. So it's a premier pattern recognition conference.
So what are we doing here?
So you have 7 conference papers, including this CVPR, and 3 journal papers, 2 information forensics and security, and 1 transaction and image processing. And all of them, they have a fact factor of 5 or 6 basically. So these are very difficult journals to publish papers in. So hopefully you will see what he has been working on for the last 5 years. There are many other things that he's worked on, but they're not included in the dissertation because there's too many things. So we tried focusing on a specific problem of novelty detection. So they'll present deep learning-based novelty detection. Okay. So about 45-50 minutes, and then we'll have question and answers.
Okay, thank you, Dr. Perera, for the kind introduction. So first of all, I'd like to welcome you all for my defense decision talk. So the title of my dissertation is Deep Learning-Based Novelty Detection. So in today's talk, first I will introduce what is novelty detection, and then I will talk a little about some of the applications of novelty detection. Then I will look into 3 specific areas of novelty detection, and I will explain in detail how we solve these 3 specific areas of novelty detection. And I will briefly talk about other things I've done in my dissertation as well. And finally, I will conclude my presentation by talking a little about future work. So we all know that classification is a well-known primary machine learning task. So when we typically learn a classifier, we learn a classifier using a finite number of known classes. So for example, if we learn a classification system to classify dog breeds, then the dog breeds we see at training are the set of known classes. So during inference, typically classifiers assume that query samples observed during inference will come from one of these known classes. But in reality, this assumption does not always hold. For example, a dog classifier, if we can present the image out of these dog classes, for example, if we consider image of a bird, that is a novel object or an open set object. So what will happen in the case of a typical classifier is that the classifier will try to classify this bird object as one of the known classes. So this is not desirable. So this is where novelty detection comes into play. So the goal of novelty detection is to determine whether a given image belongs to one of the known classes or not. So there are multiple applications of novelty detection, and I will talk about 2 applications that I actively worked during my thesis. The first application is active authentication. Active authentication is an alternative authentication mechanism proposed as an alternative to one-time authentication systems such as passwords or fingerprint-based authentications. So the idea here is the mobile device that a user is operating on will continuously collect sensor data, face images, swipe data, voice data, etc. And the biometric system will continuously authenticate the user. So as soon as an intruder starts operating the device, the authentication system has the ability to detect that and lock the device. So for example, in this screen, I've shown a typical case of an intrusion. So in the film strip, you can see from frames A to I, the original legitimate user is using the device. And from frame J onwards, an intruder starts operating the device. So we want to lock the device as soon as frame J arrives. So that's the objective of active authentication. So in this particular application, we can employ novelty detection algorithms as a possible solution. In this specific case, enrolled users becomes the set of known classes, and then the intruder classes, intruder objects, or intruder users become novel classes. So what we're trying to, when we detect novel objects, we are indirectly detecting intruders. So novel detection can be a solution for active authentication problem. The second application I will talk about is called disqualification. So this is something I worked during my internship with Adobe. So I will not get into specific details about what I did there, but Adobe had developed a new type of a tool to process PDFs, but this particular tool was only working on a certain type of PDFs. So they needed to have a mechanism to detect whether a given PDF belongs to one of the working types of PDFs or not. So if it is from one of the working types, they would proceed to apply the tool. If not, they will not apply the tool. So for this purpose, they needed to have a disqualifier, which identifies whether a given PDF is from one of the known types or not. So again, in this case, we can use novelty detection algorithms to solve this problem. Here, the compatible PDF inputs becomes known classes. All other inputs becomes novel classes. So in addition to this, there are many other applications of novel detection as well. One of them is lifelong learning. So this is where this is when a classifier identifies novel objects. They annotate the novel objects and then use it to retrain the classifier. So the classifier keep on evolving using these newly annotated samples. That's called lifelong learning. It can also be used in abnormal image detection and abnormal image detection. And also, it can be used in some of the biometric applications, such as face anti-spoofing. And also, we can study novel detection problem under different scenarios. We can study it in the case when we only have a single known class. We can study it in the case when there are multiple known classes. And also, we can study both these problems when we have some out-of-distribution data, where we can use this out-of-distribution data to simulate open set or novel classes. So in my proposal seminar, I talked about the one-class classification scenario, which is the left top corner case. In today's talk, I will be addressing the other three cases. So first, I will talk about multiple class novel detection in the presence of out-of-distribution data. So this work was published in CPR 2019 conference. So to recap the setting that we are studying this problem, here we have multiple classes, annotated data from multiple classes. So let's say we have a simple C number of annotated classes. And also we have some out-of-distribution data coming from capital C number of classes. So a good baseline for this scenario would be to train a C plus capital C classifier. We put all the data together and we train a classifier. And then we can use the class activation scores in the final layer as an indicator to perform our detection. So for an example, if the for a given input, if the output is greater than some threshold, we can say that it's a known type, known object. If it's less than threshold, we can say it's a null object because the activation, the network activation is low. So this is a good baseline that we can work with. Now, in this paper, we first identified limitations of this approach, and then we introduced a new loss called membership loss, which acts as a regularization function. And then also we introduced a method to incorporate out-of-distribution data into the training process. So first of all, let me talk about the limitations of the a naive solution. So from our discussion, it's clear that in a perfect novelty detection system, we want the network to produce low scores for open set or novel samples, and we want it to produce high scores for known classes. So when we train a network using softmax cross entropy, since softmax cross entropy is a relative measure, so we calculate cross entropy based on the ratio of the activation of the ground truth class to the activation of all other classes. So it's a ratio. So it's possible for us to get a very low cross entropy loss even if the ground truth class produces relatively lower activation value, provided that activation of other known classes are even less. So it's possible under this scenario for your known classes to produce small activations. That's the first limitation. The second limitation is that cross entropy loss doesn't necessarily penalize wrong associations as long as the correct class gets the largest activation score. So both these factors, they're not issue for closed set classification, because in closed set classification, we know that a given object is coming from the closed set of classes. So both these factors are not an issue there. But for threshold-based novelty detection, they become a problem because it violates our objective. Now, to illustrate this problem, I carried out a small experiment using VGG16 network. I took the first 128 classes from the Caltech 256 dataset, and I trained a network. And then, in this particular example, I am presenting a calculate object, which is a known object to the class or to the network. And I am visualizing how filters are activated as well as how the final logic scores are being produced. So here we see that the network is able to correctly identify that this is a calculate object because the logics of the calculator is the highest. That's very good. But we also see that other classes such as coin, dice, keyboard, they are also getting considerably high activations. But visually, we know that there's no relationship between a calculator and a coin, or calculator with a dice. So this type of association can be thought of as a wrong association. So this is not something desirable. So on the other hand, when we use the membership loss, we get something, we get the output you see in the right side of the screen. So here we get a very high activation for the calculator class, and all other classes are getting negative activations. So this is what we want, and I will explain how we achieve this through membership loss. So when we formulate membership loss, the first thing we do is we consider each output logic individually, and we pass it through a sigmoid function. So we force it to be between 0 and 1. So basically, we can interpret this operation as converting the logic score into a probability value. So then we define two risks. The first risk is the risk of associating a high score to a wrong class. So we can calculate this risk by considering these probability values, taking the summation of these probability values over all the other classes but the ground truth class. And then we define another risk, which is the risk of associating a low score to correct class. So this is 1 minus probability of the ground truth class. Then we define membership loss as the linear summation of these two loss terms. So this loss can be back propagated using this formula as well. I know it's not common to see back propagation formulas nowadays, but back in the day when we were using Café, we had to manually calculate it, so I have included it this slide as well. Okay, so with this framework, now I will explain how we incorporated out-of distribution data into our framework. So in a given network, we can identify a certain set of filters that are positively correlated with a given class. So we call them positive filters. And also the remaining filters, we call them negative filters because they provide evidence against the class. So positive filters provide evidence for the class, negative filters provide evidence against the class. So the idea here is to use out of distribution data to learn a set of filters which are providing evidence against all the known classes. So we call them globally negative filters. So how we achieve this is using a next network structure of this nature. So basically we have two parallel branches, but both these branches, the weights are tight. Basically here, what I have denoted as the reference data set is the out of distribution data set. So with respect to out of distribution data set, I am calculating the cross entropy loss. So I'm forcing the network to learn to correctly classify out of distribution data in the top branch. In the bottom branch, I'm feeding in the known set, and I'm optimizing it with membership loss and cross entropy loss. So basically, I have tied weights across these two branches so that the features we learn will have both these properties together. And during testing, we can discard the top branch and just consider the bottom branch. And basically, given an image, we can calculate the final activation features, and then check whether the maximum is greater than a predetermined threshold or not. And based on that, we can detect novelty. So with this framework, I've shown some filter visualizations. So here, for the calculator class, in the top row, you can see the most positive filters that we have identified. And by inspection, we can see that these filters capture certain structures of calculator classes. And also at the bottom, we have some globally negative filters. So these filters does not have any specific structure that can be related to the 128 classes we considered in the calculator set. They can be seen as some other, they can be seen as filters that are responsive to other structures that are not present in the known set. So they are globally negative filters. So with this formulation, I have shown a case where open set object, how open set objects will act. So in this case, playing cards is an open set object. And under the conventional CNN, we see that it activates similar filters in the filter space, and also as a result, it produces similar activations in the final activation layer. But on the other hand, in the proposed method, as I showed earlier, the calculate object now will only produce a high activation corresponding to the calculator class. On the other hand, when a playing cards object is presented, we see that a set of different filters are being activated in the filter space. So these are the negative filters that we're talking about. So they pull down the contribution of the positive filters, and as a result, the output activation map produces relatively low scores. So it's a visualization that I have to show how it works. So I tested this algorithm across 4 data sets. Caltech 256, CUP 200, Stanford dogs dataset, and founder type 200 dataset, which is a character recognition dataset. So in all these datasets, I consider the first half of the classes as known classes, and I use the remaining classes as open set or novel classes. And among the known classes, I did a 50-50 split, and I considered 50% of them during training, and I considered the rest during testing. And I also studied the impact of this method across both BGG and AlexNet networks, and I was able to produce better results in both these architectures across all the 4 datasets. Right. So then we move on to the second problem. So we considered multi-class novel detection in the presence of out of distribution data. So with a similar motivation, we try to address one class novel detection. So we published this paper in Transactions of Image Processing last year. So now, different to the earlier problem, we only have a single class. So earlier we had multiple classes, but now there's only single class, but we have some out of distribution data. So a possible application of this is abnormal object detection. So for example, during training, we are given a set of normal looking chairs in this example. So we learn a classifier that can model normal chairs. So the idea here is given an abnormal chair. So this chair in the middle was annotated as an abnormal chair. This is annotated by a human. So the idea is to identify these abnormal instances during testing. So again, in this case, there are multiple baselines that we can consider. The first baseline is we can use our out of distribution data to train CNN, and we can use its features to model the normal class. So that's letter B. And here I've also shown the TSNE visualization in the feature space. And also another baseline is to train a C+1 classifier. So we put all out of distribution data and the data from the normal class as the C+1 class, and we train a classifier there. And then we can again look at the features and try to model a one class classifier. So that's case C. And also a naive approach would be to train one class CNN using just normal data, which is not a smart idea because network doesn't learn anything because there's only one class. So if you do that, all features will get projected into the same spot, and it doesn't give any meaningful representation. So that's shown in class D. And then we have our method, which is shown in case E. So from this figure, we can see qualitatively that in our case, it's easier to fit one class classifiers because features tend to be compact. So before we formulate this problem, we identified two factors that a one class feature needs to possess. So one of them is descriptiveness. So we want the given feature to produce distinct representations for objects from two different classes. So representation we get from two different classes should look different. So that's descriptiveness. So we try to measure descriptiveness through something called descriptiveness loss. So how do we calculate descriptiveness loss is we use the learned feature to classify the out of distribution data we have at hand. So if it can classify out of distribution data properly, then we can say that its descriptiveness is high. Maximizing descriptiveness loss and compactness loss. So that's how we learn the representation. So I'm not going to describe descriptiveness loss because it's essentially cost entropy loss. But in order to compute compactness loss, we can use these formulas. So here we are essentially calculating the variance of a given feature batch, and it also can be easily backpropagated using this formula. So again, we can use this network structure to train the network. So again, we have two parallel branches with weight streets. As the reference data, we are inputting out of distribution data. From that, we are calculating descriptiveness loss. And then as the target data batch, we have the one class data we have. From that, we are calculating compactness loss. And we are jointly optimizing those two losses so that the representation we learn will have both these properties that we desire. And during testing, first we will use all our training samples from the normal or one class data to learn a classifier. And then during testing, we extract features and we feed it into the classifier to identify whether it's from the same class or not. So we tested this on 3 tasks. The first task is abnormal image detection task. For this, we used abnormal 1001 dataset. So in this dataset, I've shown some samples in the screen. So if you look at the first 3 rows, they belong, all these images, they are labeled as normal samples. In in the bottom three rows, these samples are labeled as abnormal samples. So for example, if you look at these chairs, they don't look like normal chairs. So that's why they are annotated as abnormal chairs. The second task we considered was classified as qualification. So here we're using Caltech 256 dataset, and we are considering one class at a time for training, and we are testing that against the remainder of classes in the dataset. So that's classified as qualification. And finally, we tested this on active authentication. For this, we used UMD active authentication 2 dataset. So it has 44 subjects in total. So again, we considered one person at a time, learned representation, and tried to do one class classification, considering all the other remaining users in that dataset. So in this slide, I have shown some results. So basically, we again tested this on AlexNet and VGG network architectures, and we tried variety of one-class modeling methods such as KVS neighbors, isolation forests, SVMs, Gaussian mixed models, and considering all of them, we were able to get best results in our method. Then I also considered the impact of this out-of-distribution dataset. So I tried the ImageNet dataset, Places 365 dataset, and Flowers dataset. So here what I observed was that when the complexity of the reference dataset increases, and when the reference dataset becomes more similar to your target task, the performance tends to be better. So for example, Places 365 dataset is a scene recognition dataset. So the similarity between the reference dataset and the target dataset is low. Therefore, it's what's end up producing the lowest performance. But in total, when you consider other numbers, we can see that the impact is not significant. It doesn't drastically reduce performance, but it does have some impact. And also, I considered different features, and from this, what I observed was that it's better when we use deeper features when we learn this representation. So with that, I will move on to the third paper that I'm hoping to discuss today. So this paper is accepted to appear in CPR 2020 conference. So now we are considering the classical multi-class malware detection scenario without any out-of-distribution data. So again, here we note that when we consider a representation learned through a classifier, a discriminator classifier, here we note that the features we learn are not always suitable for open set detection because they are specifically designed to discriminate between known classes. So when we learn these features, we basically discard all non-essential features that one may learn. At the same time, we also can see that these features are insufficient, even though they are good enough to classify between known classes. These features may be insufficient to capture differences between open set samples and known set classes. So in this paper, our focus is on the following. So we want to consider features that has the capacity to describe shapes, structures, and semantics of known set samples so that we have a better chance at rejecting open set samples. So for this, we used two techniques. The first technique is self-supervision. So self-supervision is a machine learning task where representation is learned through data itself. So typically, how self-supervision is done is by the user himself introducing some transformation to data and forcing the network to predict the applied transformation. So for an example, in this specific work, we used a geometric transformation-based self-supervision scheme. So here what we do is we first define a set of geometric transformations, and during training, we randomly apply these geometric transformations And then we force the network to predict the applied geometric transformation. So in order to do this, the network has to pay attention to the structure of your class objects, shape, orientation, things of that nature. So as a result, it ends up learning a very descriptive feature. The second contribution we added was something called augmented representation. So here, we first proposed to train a generative model on known classes. So since they are trained on known classes, we expect the reconstruction produced by the generative model to be good. So during training, we train the network using augmented input. So we augment the input image with the reconstructed image, and we are training the network on this augmented input. So during training, the classifier learns to associate high logic to the ground truth class, provided that there's a correspondence between the reconstruction and the input image. So in doing so, classifier indirectly takes into account disparity between the two images. So if we input the open set image, and if the reconstruction of the open set image is not very good, then since there's a difference between the two images, the classifier ends up producing a lower logic for that particular image. So this is the strategy that we propose in this paper. So to train this particular network, we have the training architecture of this structure. So this pink color network is the generative model. So we first take an input image, and then we pass it to the generative model to get a reconstructed image, and then we augment it with the input image to have a tuple. And during training, there are two forward passes. In the first forward pass, we just pass this augmented input through the network and calculate classification loss. In the second pass, we apply a random transformation on the augmented input and then pass it through the network, and we use the second branch to do the self-supervision. So the second branch is essentially doing a geometric transformation classification. And during testing, we don't have the self-supervision component. So again, we take a test input image, pass it through the generative model, get a reconstructed image, and then we augment the reconstructed image with the input image, pass it through the network, and we consider the logics we obtain through the classification branch. So when we trained the network from this, here I visualize some of the qualitative results. So in the left, I've plotted the TSNE plot for the baseline CNN and for the proposed method. So in both these cases, we can see these clusters, data clusters. So these belong to like data of different classes. But in our case, we can see that now that there's more informative features at play, the data clusters are more compact. At the same time, I've also visualized some CNN activations for failed cases for the baseline. So all these are open set samples for this considered network. And you see that all networks have ended up producing, so I'm talking about the top row of the right-hand side image. So all the cases have produced high activations, but in the revised method, we see that most of the activations are getting dropped. There are some cases where it doesn't happen, but in most of the cases it is happening. So I tested this method on two tasks. The first one is open set classification task. I basically compared this method with existing state-of-the-art methods, and we were able to get good open set performance. So here, the numbers you see on the screen are actually area under the curve of ROC curve. And also, I've listed the classification accuracy of the proposed method in this table, in this screen as well. And then we tested this on out of distribution data set. So here, the protocol is we train on all 10 classes of CPAR 10 data set, and we consider samples from ImageNet and LSUN dataset as out of distribution data. And in this figure, we are showing numbers in terms of F1 score, and we were able to get good numbers compared to previous state-of-the-art open set methods for this task as well. And also, we carried out some analysis on different architectures. So we trained our generative model, and also we changed our classifier model, and we observed what is the impact of that. So what we saw here was that when we use a better generative model, we are able to get better results. At the same time, when we improve the classifier, we are able to get better results. So that that observation makes sense with what we proposed. So finally, I will talk about two other papers that I've included in the thesis, but I will not talk about these two works in detail in today's talk. The first one is one-class novel detection. So this is something I talked about during my thesis proposal. So here, what we essentially proposed was to learn a latent representation where only a given class can be faithfully represented. So in this representation, given object from a different class, the representation still will be from the same class. Therefore, the reconstruction error will be high, and it helped us to effectively detect novel objects. And then I'll talk about our applications on active authentication very briefly. So in this paper, we considered practical problems in active authentication. So all the methods I presented today, they were basically proving the accuracy or the performance, detection performance of the algorithm. So in this paper, we considered about other practical implications such as latency and resource efficiency. So we essentially came up with a new statistic which is more robust to variations of observations. And also, this method has the ability to operate at lower sampling rate if needed. So in this figure, at the top video you see is the video seen by mobile device, and then original scores are the row scores. And you can see the row scores are varying a lot. And the bottom figure is the sampled images we get. So this sampling is done based on a statistic, dynamic statistic. And in the left-hand graph, I've shown our scores. So in red, we have the data efficient version. In the blue, we have the normal version. So in both these versions, we see that the statistic is more robust compared to the original score. And now the inclusion has happened. So there's a small latency in the data efficient version because we are taking sampled information into account. But we saw that in both cases, the statistic shoots up with a very low latency. And since it's more robust compared to original scores, it produces desirable results in practical applications. And then I will briefly talk about the work I'm carrying out at the moment. So all of them are projects that I'm currently part of. So first one is domain adaptive one-class classification. So the one-class classification schemes I've discussed in my thesis, we are making the assumption that all the data are coming from the same distribution. But it's also interesting to study what happens when there's a shift in the distribution. So for example, in this image, we have some images from web pages, and if we train a one-class classifier using these images, and if we try to recognize a real bottle in real life, the classifier fails. So in this project, I'm trying to come up with a solution to adapt this one-class classification into different domains. So the second project I'm working on is open set adversarial defense. So in this project, we are studying how adversarial attacks can affect open set scenario, and what are the possible solutions that we can bring as defense mechanisms. The third project is the anti-spoofing application. So here I've shown some real images and images from a replay attack. So a replay attack is basically someone recording face of a person through an iPad or a similar device and playing that and trying to spoof the system. So visually it's very difficult to see a difference. So what we found so far is that if we try to directly apply the open set solutions we have, it does not work in this particular case because here the similarity is very much high, whereas in open set there is a structural difference. So we need a specialized set of tools to solve this problem, so we are working on that as well. Finally, we are also working on federated learning for authentication. So this is a new learning paradigm where distributed learning can be done in a privacy-preserving manner. So we think that active authentication is an application that can greatly benefit from this learning paradigm. So that's something that we can add as well. And these are the journal publications I've published through the course of my thesis, and these are the conference publications. And I would like to take this opportunity to thank, first of all, my advisor, Dr. Vishal Patel, who's been very helpful throughout my PhD. He has encouraged me a lot and helped me a lot in my work. And also I found his method of motivating students to be surprisingly effective as well.
You're using now.
Jim is laughing at me.
And also I'd like to thank my dissertation committee members, Professor Krakran and Dr. Majid Bihar, for their comments and support. And I'd like to also thank my GBO committee members, Professor Alan Julie, Professor Gregory Hager, Dr. Mark Swensi, for their support and help. And I would like to thank both academic and non-academic staff from both Johns Hopkins and Rutgers University at this moment. And also I'd like to thank my group members who've been there throughout the years supporting. And this is one of the first group photos we took in 2015. So you all look both young and lean in this photo. After many group lunches later, not only we've put on more weight, the size of the group also has increased. So we have almost twice as many as we had back in the day. So I'd like to thank them all for their help as well. And finally, I'd like to thank my family members for continuing to support me throughout these times. So that concludes my presentation. I'm happy